so as a graph in and of its own right. And so what I'd like to look at right now is the function f of x is equal to x plus 2 times x minus 1 times x minus 4, the x minus 4 quantity is squared. Now, if you would like to, you may graph this on your calculator, but I'm going to go ahead and draw a sketch of it over here on these axes. And because of the way that this is already written so that we can immediately find the zeros of this function. We know that x equal to negative 2 is one of the zeros of our function. X equal to 1 is one of our zeros. And x minus 4 is also a 0. Well, so x equal to 4 is a 0. And I can fill in the pieces in between as well, but, and you should double check on your graph, or on your calculator, that the picture looks something like this. So it's a function that dips down, crosses the x-axis at x equal to negative 2, bottoms out, and starts to head back up, and again crosses the x-axis at x is equal to 1. Somewhere between 2 and 3, we hit the top of a hill. And at x equal to 4, because this is a double root, we end up with something that looks kind of like a parabola. So our function just touches the x-axis and then heads back upwards. So this is our function y is equal to f of x. Now, what we'd like to do is we'd like to analyze what our derivative function is going to look like. One way to do that would be for us to use our limit definition of a derivative and calculate f prime of x by looking at the limit as h goes to 0 of f of x plus h minus f of x all over h, and evaluating this limit. So the first thing that we would have to do is I go up to my original function up here, and everywhere I see an x, I'd replace it with an x plus h. And I'd write it all in. And then I'd subtract just my function f of x, and I'd divide that by h. And I'm already dreading doing that, and I really don't want to do that. And I chose this function because I want to look at a picture rather than calculate this algebraically. So calculating this derivative algebraically, using our limit definition of derivative, I do not recommend, but if you want a lot of good algebra practice, okay, so instead of calculating this derivative algebraically, using our definition of derivative, which seems like a really bad idea, we're going to sketch a picture of what f prime of x looks like. So given our original function, we're going to come up with a decent sketch of what the derivative function is going to look like. So what I'll do is I'll start by matching up my axes. And making sure that I have the exact same tick marks on my graph. This is going to be y is equal to f prime of x. Now, my x-axis, I want those values to line up exactly. The y scales, they can be very different, and that's okay. But the x-axis should line up exactly. Okay, so when we saw this picture over here, where we had a derivative function, and it was describing the slope of the original function f, well, we saw a few things. In particular, when our original function was flat, our derivative, f prime, had a 0, meaning our derivative touched the x-axis. So let's go ahead and identify where that happens over here. Over here, I see a couple of flat spots on my original function f. I see one right here, bottom of this valley. And so that flat spot corresponds to f prime being equal to 0. And I see another flat spot up here at the top this hill. If I draw a tangent line, the slope of that tangent line is 0. So the height of my derivative graph is 0. And there's one more flat place, and that's this valley over here that's touching the x-axis. So right at x equal to 4, our derivative is equal to 0. Okay, so I'm using these dashed lines as guidelines. I'm going to extend them downward. It's useful to have graph paper to do this, but I don't have that for the whiteboard, so check paper. Okay, now let's take a look at this middle section here where our function is going from this bottom of the valley to a top of the hill. So as I'm reading from left to right on this middle section here, f is increasing, moving uphill. So what does that tell us about the slope of f? Is that slope positive or negative?
Positive.
Positive slope, which tells us that f prime will be above the x-axis. All right, so f prime is describing the slope of the original function, so f prime will be positive. Now, looking at this picture here, starts out and we have a slope that is, if I kind of imagine a slope here just a little bit to the right of our flat spot, positive slope, but a very small number. And as I move my pen along, my pen is growing steeper and steeper until I hit somewhere around in the middle here. This is about the steepest place in between our bottom of our valley and the top of our hill. So the place where f is steepest will have the largest slope, which tells us that f prime is highest at that point. So some tools that we've been using. F is flat, corresponds to f prime has a 0, meaning f prime touches or crosses the x-axis. When our function f is increasing, this corresponds to f prime being above the x-axis, aka positive. And when f is steepest, f prime is farthest away from the x-axis. Okay, so let's analyze this second portion here. So we've got this other portion of the function where we've got from the top of this hill to the bottom of the valley, f is decreasing. It's going downhill. So that tells us that the slope along this portion is negative. So our f prime graph, which is describing slope, is going to be below the x-axis. So when f is decreasing, meaning moving downhill, that corresponds to f prime being negative or below the x-axis. All right, so we know that we're down in this section right here below the x-axis. And if I look on this region that we're talking about, the steepest place, the place where if I was sledding down this hill, the place that would give me the best bang for my buck, is right here in the middle. Okay, that's about the steepest I'm going to get. And so that is the steepest, but it's a negative steepness, okay, because it's downhill. It's our sharpest descent. Okay, and so our steepest point in here will be when f prime is farthest from the x-axis. All right. Now, from our bottom of our valley here off to the right, our original function f is moving uphill, increasing. So the slope of f is positive. Tells us f prime is positive, tells us f prime is above the x-axis. And as we walk farther and farther to the right, what is happening to the steepness of this graph? Yeah, it's getting steeper and steeper and steeper. So it tells us that our derivative is getting larger and larger and larger. Our derivative function is moving farther away from the x-axis. All right, are there any questions on these three sections so far of our f prime graph? Okay, so we still have the farthest to the left over here, and so thinking about that as I'm moving left to right, this part is all downhill, so all decreasing. Okay? So our f prime graph will be below the x-axis, and farther to the left, our graph is very, very steep in the negative direction. Okay? And so that means that our f prime will be far away from the x-axis, below the x-axis. And so what we've drawn here is a picture of what f prime looks like. Are there any questions about that picture? Going once. Going twice.
So is it the, I don't know how to explain it. It's almost like the reflection when you flip it the other way.
It looks like a sine cosine.
Yeah, I thought it was like sine going to cosine, but.
So